right, well, this is our last real chapter. Isn't that exciting? We've made it. Going to talk about aliphatic and Aryl amines. And again, starting off with good news, you actually know most of the reactions of certainly aliphatic amines, and there's really only one class of reactions of Aryl amines that we're going to have to look at. Amines are basically the organic analog of ammonia, okay? You take an amine of some sort, a nitrogen with two hydrogens. Remember, it has a lone pair of electrons. That's where most of the reactivity lies. And you have some carbon thing attached to it. Compounds of note. This is amphetamine. Very, very simple compound, as you might see. Very easy to make, actually. This is cocaine. Now, note the bicyclic ring structure here. Remember how much trouble you had drawing these. This is a six-membered ring in a chair. Nitrogen's in the ring. And we have a two-carbon bridge going around. This guy down here is very complex. This is strychnine. You may not know strychnine. When I was a child, you could just go in the drugstore and you could buy it. Strychnine is very, very poisonous. It's used to kill rodents, spouses, things like that. Rumor is that Alexander the Great was poisoned using a little bit of strychnine. Actually, it only takes about 100 milligrams to kill somebody. That's about the size of a pea. So very, very poisonous stuff. You can't go in the drugstore and buy a bottle of it like this anymore, but actually you can walk into Walmart and you can buy strychnine. It's called children's cold calm. Yes, children's. Virtually everything in this preparation here is one of these poisonous alkaloids, including strychnine, manufactured by a French firm. The reason that it exists is that it is a homeopathic medicine. Homeopathic is a fancy word for there's nothing in it. So it's basically just water, and that's why it has no regulation, and they can sell children's cold calm that actually does contain maybe a molecule of strychnine in the whole bottle, but not much. That's good. When you are naming amines, because our nitrogen is trivalent, we can have two alkyl groups. We can have one. This is dimethylamine. This would be trimethylamine. If we replace all four valences, we make a cation, just like the ammonium cation. And this is the tetramethylammonium chloride. This is the cation. Of course, it must have an anion. Here we have a couple methyls, and we have a propyl group, so we can mix it up any way we want. Benzylamine is a very common amine, very easy to work with, also called phenylmethyl and amine. We'll talk about nomenclature in a minute. Depending on how many things are attached, we call amines either primary, secondary, tertiary, or quaternary. Again, that's very simple. It's just the number of carbon things that are attached to the nitrogen. Any questions? All right, nomenclature. We're going to drop the E and we're going to call it an amine. Now, an amino group is a very low priority substituent. It is slightly higher than a simple alkyl group, but not much. So it's a very low priority. Nonetheless, you want to give it, the longest chain should contain the amino group. We want to begin at the end nearest to the amino group if we can. And we need to give the lowest number at the first point of difference regardless. So the same basic rules. Like I say, the amino group is just slightly higher priority than, say, a methyl would be. Look at some examples here. Look at these and think out how you might name them. Step 1, you want to find your longest chain containing the amine. You want to give it the lowest number. Take the parent hydrocarbon, drop the E and add amine to it. So for our first guy, we have a 1, 2, 3, 4, 5 carbon parent. So it's going to be a derivative of pentane. We want the amine to have the lowest number, so we'll make this carbon 1. Our name would therefore be pentanamine with a methyl group here in carbon 3. Stringing it together, 3-methyl, 1-pentanamine. AN tells you there are no double bonds. The amine, of course, is that it is a simple aliphatic amine. You can also use the amino nomenclature. So we would just call this a pentane. We could do 1 amino, 3-methyl pentane. So that works fine too. Do the same thing with this guy now. Step 1, find your longest chain. Want the amino group to have the lowest number. Name it as a derivative of the hydrocarbon, and then stick the methyl group in appropriately. Our longest chain is going to be 1, 2, 3, 4, 5, 6 carbons. So it's going to be a derivative of hexane. Our amino group is in carbon 2, so it's a 2-hexanamine. And we have a methyl group here, out here in carbon 5. We want to let this be carbon 1. It's a tie. Methyl, if we started at this end, the methyl would be on 2. Start on this end, the amino is on 2. If it's a tie, the amino group wins. Yeah?
I had a question. Why wouldn't you have carbon number 2 be 1 and have a methyl group on number 1, like so that the amino group would be number 1 also?
Right here?
No, on the other.
On this guy?
No, on the one that we're doing.
Oh, okay, this guy.
Yeah, on.
Oh.
Yeah, like why wouldn't it be there and you would have
Well,
a methyl?
again, you always want to find your longest continuous chain.
Okay.
That's our first standard rule for everything. So, let's see. This is going to be a 5-methyl, 2-hexanamine. Our last one here. Go ahead and apply the rules. Find your longest chain. Decide where carbon 1 is. It's going to be a derivative of 1, 2, 3, 4, 5, 6 again, so it's going to be a derivative of hexane. Our longest chain looks like this. If we let this be carbon 1, that means our amino group would be in 2. Then our numbering would be 2, 4. If we let carbon 1 be down here, our numbering would be 2, 3. So this is a case where the amino group loses and the lowest number sequence wins. So it's going to be a hexanamine. The amino group is going to be in carbon 5, and we have methyls in 2 and 3. 5-amino 2,3-dimethyl hexane, or, no, This is it.
Why would it be that way?
This is the name you would get if we started numbering here.
Well, why did we switch the rules to start numbering at the other end?
I'm sorry, what?
Why didn't we just start numbering at that closer to the main group?
Well, because if we start numbering here, our number sequence would be 2, 4, 5, right? If we start numbering here, we have 2, 3, 5. 2, 3 is lower sequence than 2, 4. Any questions? Let's make it a little more complex.
What?
Our parent here is obviously going to be our cyclohexane ring. Now, both amino groups are equatorial, aren't they? They're 1,3 diequatorial. We refer to that stereochemistry as cis or trans. It's a cis, right? They're both on the same side of the ring plane. This is going to be a 1,3-diamino cyclohexane, and we do have to include the stereochemistry. Now this is a case where we're going to look for the longest chain containing the amine, and we're going to treat our phenyl group as a substituent. So our longest chain is going to be this guy, giving the amine the lowest number. This would be 1, 2, 3, 4, 5. So it's a pentanamine. It's a 1-pentanamine. And we have a phenyl group here in carbon number 4. 1, 2, 3, 4. 4-phenyl 1-aminopentane or 4-phenyl pentanamine. And our last guy. Remember back in the old days when we did nomenclature of rings, it was a dead giveaway. If we had two things on one carbon, it was going to be carbon number 1. Well, again, the amino group loses out to the fact that our number sequence here would be 1, 1. Therefore, we're going to let this be carbon number 1. It's going to be a 1,1-dimethyl 4-amino cyclohexane. Any questions? Now, nomenclature, as always, is a fairly minor part, but do make sure that you know the basic rules. This applies for the entire exam and final. Make sure you know the basic rules of nomenclature of all these guys. Any questions? All right, bonding. Nitrogen has a valence of 3. This is an sp cubed carbon, however. It's sp cubed because, remember, we have the lone pair here. And so this is pretty much tetrahedral. Our bond angles are just about 109 degrees. This is a secondary amine. We have a hydrogen, a methyl group, and an ethyl, and of course our lone pair. Now the fact that we have a lone pair here means that this nitrogen can undergo inversion, spontaneous inversion. What it looks like is something like this. As this nitrogen flips back and forth, the lone pair occupies a position down or a position up. The barrier for the inversion here is very small. So at room temperature, this thing happens, 10 to the 6 times per second. Obviously, if we had a fourth carbon or something here, that would be different. It would not invert, but as long as we have the lone pair, inversion happens constantly. Pyramidal inversion is the actual term. Now there's a very interesting thing that happens because of that. If you look at this compound, counting the lone pair, we would have 4 different substituents around a tetrahedron, wouldn't we? Remember back in chapter 5 when we did stereochemistry. This is lowest priority, then this guy, then this guy, this one. This structure that I've drawn here would have S stereochemistry. However, remember back when we did SN2 reactions, we also had inversion, didn't we? The nucleophile came in, leaving group left, and when that happened, our stereochemistry swapped. So when we do pyramidal inversion, to give this guy, we wind up now with R stereochemistry. So that means that if we have a nitrogen with a lone pair, we can have R and S isomers. However, the inversion is so fast that you can't isolate them. Any questions?
So it inverts 1,000,000 times a second, you're saying?
Yep. About 10 to the 6 times per second. Now nitrogen has this lone pair. And because of that, it can be a hydrogen bond acceptor. It also can have a hydrogen on it, which makes it a hydrogen bond donor. Because of that, amines tend to aggregate, just like alcohols and water, and they form networks of hydrogen bonding. Because we only have one lone pair to work with, unlike an oxygen, we can have 2 hydrogen bond donors here, but only 1 acceptor. So this hydrogen bonding is not as good as it is in alcohols, and certainly not as good as it is in water. Nonetheless, based on their molecular weight, amines have fairly low boiling points and melting points, and that's due to this hydrogen bonding stuff. Any questions? Well, the other thing that amines can do is they can ionize. If we start off with an ammonium cation, that can lose a proton and form the free amine and generate hydronium. So going all the way back to general chemistry, we can write this equilibrium. And of course, this is the equilibrium for the acid dissociation. The expression is going to be products over reactants. We ignore water. Let's ignore that water. We have products here, the free amine, we have hydronium, and we have the ammonium cation. This equilibrium constant, without the water, I apologize for putting that in there, is about 4 times 10 to the minus 11. Now, what does that mean in terms of an equilibrium? That means that most of the stuff here would be wrapped up as reactants. It's a very small number, so we have a very small amount of this. That's a small number, and we have lots and lots of this. Whenever we have a Ka, we convert it to a pKa. Remember our rule for pKa's. The smaller the pKa, the stronger the acid. Let's just look at a representative list. The one that we just did was ethylamine with a pKa of about 10.5 or so. As we put electron withdrawing groups on the ammonium cation here, what we're doing is we're stabilizing the anion. Not the anion, I'm sorry, the neutral form. Another way to think of it is we're destabilizing the cation. We put something, it pulls electrons away, it makes this up here less stable than this guy. That tends to make it a stronger acid. So electron withdrawing groups on an amine destabilize the cation, stabilize the neutral form, and we get a lower pKa, simply a stronger acid. Any questions?
I thought that, what's the relationship between the stability of the cation and the strength of the acid? Because I thought that it was the other way around.
Well, if you look at the equilibrium here, okay, think about what's going to shift this equilibrium. If this is very, very, very stable, then it's going to go on this side, isn't it? If we make this less and less and less stable, it's going to make this relatively more stable and shift the equilibrium this way. It's a simple Chaplain effect. Yeah, Joe.
Whenever you refer something as a molecule or chemical with the electron withdrawing, are you saying that the dipole shifts to a greater, like red color? Is that how you should think about it?
Right. If we looked at these in terms of electrostatic potential maps, the ammonium, mostly this carbon we'd be looking at, would be blue, right? This next to the ammonium. If we go and we put electron withdrawing groups on it, that's going to make it even bluer, which makes the ammonium a stronger acid. All right, we talked about simple lesson 2 reactions from the past. We know that nitrogen is a fine nucleophile. It has this lone pair of electrons. And if we take it and we dump in something like bromomethane, we can get a very simple happy SN2 reaction where the lone pair attacks, the bromine leaves, and we wind up with, in this case, the methylamine. We also lose an HBr. Now, if you think about this, once we lose the HBr, this is a free amine again, isn't it? If this is a free amine and we have bromomethane around, the whole thing can happen again. And suddenly we have a secondary amine. If it goes and loses its proton, we have another pair of electrons we could use, and we would make a tertiary amine. And finally, if we did this one more time, taking the lone pair of electrons here, we would wind up with the ammonium cation. This is referred to as exhaustive methylation, because you get exhausted doing it, I guess. You methylate all the sites that you can on your amine or on ammonia. We'll do one reaction in a little bit where the first step is to do exhaustive methylation. That's the Hoffmann elimination. This is mostly a nuisance, however, because let's say that you really wanted to make methylamine. This is a lousy way to do it, because as you make this, you're just going to make these guys at the same time. In fact, if we take, this is in 1-bromo-octane and ammonium, the simple primary amine turns out to be about 45% of the product, and you get roughly the same amount of the secondary amine. Tertiary amine, you get less. Quaternary ammonium salt, we get even less than that. Most of the product is primary and secondary, but still, if you really wanted it, you'd get 50% yield at best. There's a way around this, however. There are 2 ways we're going to learn, at least 2, maybe That is, instead of doing our simple SN2 reaction with ammonia, what we're going to do is use azide, N3- as our nucleophile. Now this gives us an intermediate, alkyl azide. Azide, in a second step, we dump in lithium aluminum hydride, reduces the azide to the amine. If we do this method instead of the one we saw before, we get 100% yield of the primary amine. So if you want to make a primary amine, you don't want to do a simple SN2 reaction with ammonia. You want to do azide and then reduction. The mechanism, just in case you're wondering, we start off with our alkyl halide, and we have N3-. N3- is a very fine nucleophile. It will attack, the bromine will leave, and we make the alkyl azide. This is the thing that we reduce with lithal. This nitrogen goes to the amine, and we lose these guys. It's a nice reaction. It's very simple. It's not something that you would ever do here. Alkyl azides can be extremely explosive. Any questions? Well, that's one way to get around the problem of multiple substitution. The other one is to use what's known as a phthalimide synthesis. Back when we did carboxylic acids, I told you that benzene 1,2-dicarboxylate was called phthalic acid. Trivial name, been around forever. If you make an amide of that twice, it's called an imide, I-M-I-D. Nice cyclic compound. This hydrogen, because it's next to two amide carbonyls, is actually quite acidic. So if we take this and dump in a little bit of potassium hydroxide, we go virtually 100% to the anion. This is what we're going to use as our nucleophile. So we take this stuff, dump in our alkyl halide, simple attack, leaving group leaves, and now we have our leaving group attached. We still have all this other crap attached too, don't we? How do we get rid of that? Well, it's an amide, isn't it? We know we can hydrolyze an amide back to the acid, either with strong acid or strong base. Let's just use strong acid here. We wind up with phthalic acid, and we now have our primary amine. Phthalimide synthesis works very nicely, not explosive. It does all the things that you would like it to do. Any questions? All right, so two simple ways to get around multiple substitution. One is to use azide and reduction. Other is to use phthalimide and then hydrolysis. All right, this guy is dopamine. You've probably heard of it. Let's make dopamine using a simple azide synthesis. Now remember, you want to work backwards. So the compound that you want to write down here somewhere is going to be the alkyl azide that you would then react with lithal. The alkyl azide, remember azide is N3. This is going to be the last nitrogen in the group. And so we could simply write this way as our alkyl azide. last nitrogen in, we're going to reduce with lithal. Now, how would we make an alkylazide? We would simply take azide anion and react it with an alkyl halide. The alkyl halide we need, instead of the N3, we would simply need a leaving group, something like bromine. And that should do it for you. Any questions? All right, let's do the same thing with a phthalimide synthesis. In the phthalimide synthesis, this nitrogen was the imide nitrogen. So we had an amide carbonyl on both sides attached to the benzene ring. And so it looks something like this. Amide carbonyl, 1,2 on the benzene ring, and that's our nitrogen right there. We got rid of all this just with simple acid hydrolysis. In order to make this, we had to take the imide anion, react it with an alkyl halide. So where the nitrogen is attached, we simply need a leaving group. Again, the same alkyl bromide would work. Want to react this with the imide anion, make this, and then hydrolyze. Nice, simple set of reactions. Any questions? All right. We already know at least 2 ways to make simple amines, primary amines. We learned these back in chapter 20 and 21. We know that if we have a simple, well, tell you what, I'll let you do it. Come up with 2 other functional groups that can be reduced by lithal to give us dopamine. Our first one was from chapter 20. Chapter 20 was entitled Carboxylic Acids and Nitriles. That's a hint. Nitrile contains a nitrogen, doesn't it? And one of the reactions that we know of nitriles is that they can be reduced smoothly by lithal to give the corresponding primary amine. Chapter 20. Chapter 21, we talked about acyl derivatives, carboxylic acid derivatives. What is the carboxylic acid derivative that contains a nitrogen? Quite simply, that is an amide. If we take an amide, reduce it with lithal, a carbonyl goes to a CH2, and we get the primary amine. There's one other way to do this that we'll introduce, and it's called reductive amination. It's kind of a neat reaction, actually. In reductive amination, you're going to take a carbonyl compound. In this case, we want to use an aldehyde. We're going to react it with ammonia. Now, you can actually use any amine, but in order to make dopamine, we would need an aldehyde and ammonia. And we do this in the presence of Raney nickel. Remember, Raney nickel is finely divided nickel that has hydrogen adsorbed to it. So it's a simple reducing agent. What happens here is the nitrogen attacks the carbonyl, and we form an imine. This is an equilibrium. The ammonium cation is very reactive. In the presence of Raney nickel, this will be reduced. This becomes a CH2, and we make our primary amine. Called reductive amination. In a much gentler form, you could use any carbonyl, aldehyde or ketone, and we could use any substituted amine as well. So that's kind of neat. We have a substituted amine, we wind up with a substituent out here, don't we? Any questions? We also know that amines react with carboxylic acid derivatives, and this gives us amides, doesn't it? Very simple reaction. Here's an acid halide. Our amine is going to be the nucleophile, going to attack the carbonyl. Our best leaving group is going to be our chlorine, so it's gone. And we simply make our amide. Again, this is a reaction that we talked about way back in chapter 21. There's a similar reaction that you can do not with an acid halide, but with the sulfur analog. It's called a sulfonyl halide. So instead of a carbonyl here, we have an SO2Cl. It's the same basic mechanism. The nitrogen is going to attack the sulfur, chlorine is going to leave, and we make what's called the sulfonamide. So very, very similar chemistry to what we learned back in chapter 21. Now, why should you care about sulfonamides? Ever heard of sulfa drugs? Back in the 30s, the good chemists at Bayer in Germany developed this guy. This is the first real available antibiotic. And actually, sulfa drugs, derivatives of this, are still widely used today. We'll also look at this general structure a little bit later. This comes about from what's known as a coupling reaction, where we attach our nitrogen between two benzene rings. Very simple reaction, but this is the original sulfa drug.
What does that do to the bacteria, Dr. Young?
Well, it interferes in, what's the pathway? I'm pulling a blank. I pulled a blank.
Okay, we'll get back to it right now.
Do you remember?
Metabolic pathway?
Yeah, it's, I'll just put it on the test, okay? Sulfonamides are also very useful. Remember we talked about qualitative organic chemistry, where you have a compound and you don't know what it is. and you do some very simple tests. We did the Collins test to see if it was an aldehyde. We did the iodoform to see if it was a methyl ketone. Well, you can actually make a sulfonamide and determine whether or not your unknown is a primary, secondary, or tertiary amine. That's not easy to do otherwise. What you do is you take your unknown, in this case it would be dopamine, react it like we did, and we make the sulfonamide. Now, the hydrogen on this nitrogen is acidic, just like it was on phthalimide. This, in the presence of base, this is the bond we made, just so that you know. This hydrogen is acidic, so in the presence of base, we pull it off, and we make a salt. Now, just like any other well-behaved salt, this is soluble in water, at least soluble in base. So, if we have a primary sulfonamide, which means we had a primary amine, we would get a base-soluble sulfonamide. If we happen to have a secondary amine, so the methyl group here instead, there's no hydrogen to pull off, is there? So you go and you dump this into base, and nothing happens. That tells you that we have a secondary amine. Finally, if you have a tertiary amine, so we had two things on our nitrogen, you could not make a sulfonamide at all. This is called the HINSBERG test. Something to remember. Sometimes name reactions like these show up on standardized exams. Very classic name reaction, the HINSBERG test, primary, secondary, and tertiary amines. Any questions? Now remember I said exhaustive elimination. This is, or exhaustive methylation. This is the HOFMANN elimination. Again, it's a name reaction, and it has one peculiar feature that makes it a good thing for a standardized test. If we took our dopamine here and dumped it in with a ton of bromomethane, we would, like we saw in the earlier slide, methylate this nitrogen 3 times, 4 times, or 3 times, to give us the quaternary ammonium bromide. So we made a quaternary ammonium salt. We let the thing go until we get exhaustive methylation. This trimethylamine is a very good leaving group now. So, if we took our stuff and we treat it with base, now the base we want to use is special. It's silver oxide. Actually, that forms hydroxide in solution, but the silver plays a role here too. So in the presence of silver oxide, we're going to pull off the beta hydrogen here. This is it. Hydroxide will pull off this hydrogen. Our trimethylamine leaves, and we have an alkene. So this is an E2 elimination. So the Hoffmann elimination is just a way to take an amine and convert it to an alkene. But the one thing that makes the Hoffmann really unique, and the one thing to always remember about Mr. Hoffmann and his elimination, is it doesn't follow Zaitsev's rule. Zaitsev's rule tells us that we should do an elimination here to get the most highly substituted alkene, right? Hoffmann elimination instead gives the least substituted alkene. So that's the one thing, that's the one unique thing that you need to remember with a Hoffmann elimination. Zaitsev was German. Hoffmann is obviously, I'm sorry, Zaitsev was Russian. He's German. They didn't get along. So that's how you can remember. Hoffmann also has a rearrangement. Now this is kind of magic, but if you take an amide in the presence of base, bromine, and water, now we're not going to write a mechanism for this because I don't want to. What happens is we're going to lose CO2, comes fizzing out. The nitrogen migrates to the point where the amide was attached, and we get the amine. Hoffmann rearrangement. Curtius also has his own rearrangement. This is an acyl azide. Now, how would you make this? You would take an acid chloride and add azide, wouldn't you? Chlorine leaves, and we get this stuff. Then you take this, you warm it up, and if you're lucky, nitrogen and CO2 will come bubbling out. Again, this nitrogen migrates to the point of attachment to give the amine. The only real problem with acyl azides is that, just like most azides, except more, these are extremely explosive. When I was in graduate school, there was a guy trying to use the Curtius rearrangement to make a penicillin beta lactam. That's a 4-member ring, amide. So the idea was this would eliminate nitrogen, go back, make the 4-member ring. Prepared his little tube of this stuff and was very proudly holding it in front of everybody. Happened to set it down, walked here to there, and it just went off like a balloon. Good thing he wasn't holding it, right? So very, very unstable compounds, very dangerous, especially since you have to heat it up. All right, we always do spectroscopy. We already know about spectroscopy of amines, or at least mostly. We know that in the region around 3400-ish, that's where we get OH and NH stretching. We can get symmetric and asymmetric. That's why there are kind of two little peaks there. This is our classic looking NH stretch. But there's one other peak that also shows up, and this is the NH bend. Now the NH bend comes right about 1600. It's not really intense, and it's a little bit broad. So it looks like a very weak excuse for a carbonyl that's way too low. That's how you can pick it out. NH bend, you expect it to be around there. Don't confuse it with a carbonyl. Remember, a carbonyl will be higher, and it will be much more intense. Any questions? All right, well, let's take this and let's figure out what this compound is. This compound has a molecular weight of 107. It is C7H9N. Degrees of unsaturation. Remember your rule with your nitrogen. We have to subtract a hydrogen for every nitrogen. This gives us 4 degrees of unsaturation. All right, so we're probably looking at a benzene ring, right? That makes sense. Now, when we have a benzene ring, there are things that we look for in the mass spec. In our mass spec, this is clearly our molecular ion at 107. We're managing to pull off a hydrogen and make a base peak at 106. What we don't see in here is a significant 91. Now, 91, remember, is tropylium. And if we can cleave out tropylium easily, we expect to see it. We see 77 down here, which is just the bare benzene ring, but no real tropylium. So we have an N-1, that's loss of a hydrogen, but we don't see a tropylium for some reason. All right, we'll just leave it at that. Go back to the IR. Our standard analysis here, we'll start at the high end. 3400, we have a very nice NH stretch. We know it's on an OH because there's no oxygen in the compound, is there? So this tells us that we have an NH in here. On the high side of 3000, we have a nice little sharp peak, sp squared CH. On the low side of 3000, 2900 or so, we have nice peaks suggesting sp3 CH. Look at our triple bond region here at 22-ish. Don't see anything. Look at 1700. That's right here, that little dotted line. That's about as low as you're going to get a carbonyl to go. No carbonyl. That tells us we're not dealing with an amide, right? And finally, here is 1600. We have what we will call our NH stretch. And we also have peaks here that we often see with benzene. Remember, benzene typically has a sharp peak at 1600, but we can't see it here. But it also has these others going down to about 1450. We can look at this and say, this looks like a benzene ring of some sort and an amino group. Everyone happy with that? All right. Let's look at the NMR. We expect a benzene ring, don't we? And my gosh, here at 7.1, we have a beautiful, sort of beautiful, peak with 5 hydrogens. That would be a mono-substituted benzene, wouldn't it? Now we have 2 singlets down here, and they're both worth 2 hydrogens. Is that 2 CH2s? Well, we've only got 9 hydrogens in our compound and 7 carbons. So this is 6 carbons here. One of these is a CH2. What's the other one? Got to be an NH2, doesn't it? Can't be a CH2. One of these is a CH2, that's this guy. The second one here that is shifted up to almost 4 is going to be our NH2. This thing down here, our rough singlet, is monosub benzene. Let's confirm that with a C13 NMR. In the benzene region here, we have a singlet and 3 doublets. What is that? Monosub benzene. And we have 1 triplet, that's a CH2, down around 50-ish. We don't see the NH2, do we? Because this is carbon NMR. So we have a simple CH2 and a monosub benzene. So let's take our pieces then and put it together. We really know that we have a monosub benzene, right? We know we have a CH2, So we could like stick it on here. That leaves us, in our analysis, 1 nitrogen and 2 hydrogens. That's the NH2. There is only one way in the world you can put these little guys together. And that's to make benzylamine. Now, you should sit and say to yourself, I hope you are, if this really is benzylamine, why don't we see tropylium? What's happening here? Well, when you form the radical cation, the molecular ion, amines tend to undergo loss of a hydrogen. The reason, in this particular case, is once we lose our hydrogen here, we can form the ammonium cation. This is what the peak is at 106. This is our base peak. There is no way, simple way, because we've already lost this hydrogen, there's no way we can clip off the amine to make tropylium, is there? All we can do is clip off here and make our peak at 77. Primary amines especially tend to lose a hydrogen right next door to the amine to form this. So you see a lot of M-1s. And then we get a cleavage on the other side of that quite commonly. So even though it's benzylamine, you don't see tropylium because we've already lost the hydrogen. Any questions? All right, well, this is just simple review. Go ahead and quickly just write down generic products for these generic reactions. Our first reaction, we simply have an amine reacting with an alkyl halide. We know that this is a really messy reaction because we can get multiple substitution. But our first product would be just the simple substituted amine.
If we ever saw that on an exam or whatever, would you like this to just...
Well, you wouldn't see this. There would be, like real groups here and there. If I gave you a simple primary amine reacting, yeah, this is the product you should put. If I ask you, is this a good way to do it, you should say no. Our second one, this is an acid halide or anhydride. Could be a mixed anhydride. We know from back in chapter 21, this is going to go, we're going to attack a carbonyl, leaving group will leave, and we will make the amide. Chapter 21. This is reductive amination in a more general form. Our nitrogen is going to attack the carbonyl. We're going to form an imine. So the nitrogen atom is going to be where the oxygen is. Then we reduce and we make a substituted amine. Very general reaction. Again, this is the bottom part. This is where our carbonyl was. And we just added this in place of the oxygen and then reduced it down. Reductive amination. And to make sulfonamides, just like we did up here to make regular amides, nitrogen attacks the sulfur, chlorine leaves, We get a simple sulfonylate. Couple more simple ones. If we take an amine, react it with a carbonyl, as we just saw, we would make an imine, right? Carbon-nitrogen double bond. However, this is a secondary amine, isn't it? So that means we would have the ammonium cation. Now, way back in chapter 19, I believe, we saw that if you take a carbonyl and react it with a secondary amine, we make an enamine. Remember, this is the same thing that happens in aldolase, where the nitrogen comes from the enzyme, form the amine, secondary amine. This then forms an enamine, and that's our nucleophile. Mr. Hoffmann and his elimination. Don't have to worry about the anti-Zaitsev rule here, because we can't really tell what's attached, but we know that all that's going to happen is we're going to do an E2 elimination here and make the alkyl. This is what the phthalimide synthesis looks like, isn't it? Think about the steps. Step one, we take phthalimide, react it with hydroxides. We have an anion right here, don't we? That's our nucleophile. Second step, we're going to react this with an alkyl halide. So the N- will attack, halogen leaves. Third step, we're either going to use acid or base to hydrolyze off the amide, and we would get the simple primary amine. Simple alkyl halide reacting with sodium azide. Azides are nucleophile. We're going to wind up with an N3 right here, aren't we? When we reduce it, the last nitrogen remains, the others go away, and we get the simple primary amine. Chapter 20, nitrile plus lithyl. We're going to reduce so that this carbon becomes a CH2, this carbon, or this nitrogen becomes an NH2, and we get the primary amine. Chapter 21, we saw that simple amides also underwent lithyl reduction. Carbonyl becomes a CH2, and we get the simple amine. Now this next one looks bizarre. You have to remember it, okay? This is Mr. Hoffmann's rearrangement. It's odd conditions. Base, bromine. What happens in the Hoffmann rearrangement is that we're going to lose CO2, aren't we? So this carbon goes. whole carbonyl goes. And the nitrogen just simply moves over to where the carbon was attached. And finally, in the Curtius rearrangement, just like Hoffmann here, we're going to lose the carbonyl as CO2. This nitrogen is going to wander over where the carbonyl was attached, and we will make this nitrogen gas, CO2, but again, our primary amine. Hoffmann rearrangement, Curtius rearrangement. So this pretty much summarizes everything that we know and everything that we just learned about simple aliphatic amines. Let's do Aryl amines. Aryl amines are special. If it wasn't for aniline, this stuff, there would be no organic chemistry. Yeah.
Aliphatic have to do with like an open chain
I'm sorry?
Aliphatic, the term.
Aliphatic, we have a simple saturated Aryl, we're attached to a benzene ring.
Got it.
Organic chemists used to be a struggling brood of people. You know, nobody really cared much. Mostly trying to figure out biochemical pathways and sugars and stuff like that. But there's no money in that. And then one day, this guy named Perkin was fishing about in his tube full of tar, and he came up with this stuff. 3-amino, 2,8-dimethyl, 5-phenyl, 7-phenylamino, 5-phenazinium chloride. All right. Not much of a name for marketing, right? So he found this stuff, decided that it was neat, and gave it a separate name. The name was based on the color, and the color was mauve. This was very, very exciting in the mid-1800s because nobody liked wearing white shirts and stuff like that, so you had to dye them, right? How did you dye stuff in the old days? You use indigo, you use plant extracts, you use beets, coffee, whatever. This was a synthetic dye that you could sit there and make. Now the indigo market was very popular. Lots and lots of demand for indigo. It's actually a very, very nasty story. It's tied into the slave trade worldwide. Huge farms of slaves making indigo. This you could make in a test tube. Perkin realized this, commercialized it, and made an absolute ton of money. There are other compounds that are similar to this. This is called methyl yellow. It's actually used as an indicator now. But you'll note that these are all simple derivatives of aniline. Aniline was the stuff that suddenly made organic chemistry profitable, made Perkin rich as all get out. The Chemical Society in London is still called the Perkin Society. All because of these synthetic dyes. Well, the synthetic dyes, like I said, are based on aniline. Aniline, just like toluene, is accepted as a parent by IUPAC. So instead of aminobenzene, we can call this simply aniline, and then name substituents based on it, 4-bromo, 3-bromo, 4-chloro, whatever, aniline. We can also substitute the nitrogen here. This is N-methylaniline, and N-dimethylanilin, and this is trimethylaniline chloride. All right, the reactions of aniline are basically just the reactions of the amino group here. So everything that we've talked about, almost everything we've talked about, works here. Okay? Yeah.
My Q is what is this N?
N-methyl,
What does that mean?
N-dimethyl. This means the methyl is attached to the nitrogen.
It's not a number because there's no carbon.
But,
Oh.
Why does the last one say chloride?
but there's one chloride
Oh.
that says cation. But there's one reaction of aniline that is entirely unique. And this is what Perkin and all of his friends used. And this is to make a diazonium salt. If you take an amine, such as aniline, Aryl Amines, react it with nitrous acid, HNO2, in the presence of something like sulfuric or hydrochloric acid, what you do is convert the amino group into a diazonium salt. This is actually typically done with sodium nitrite, just in an acid. A very, very simple reaction. Goes very, very smoothly to give the diazonium. Now, you don't ever really isolate and play with the diazonium. But if you think about it, these two nitrogens really dearly want to be nitrogen gas, don't they? Yeah, they do. So that makes this carbon down here very reactive. Diazonium salts. If we treat a diazonium salt with hypophosphorus acid, no, that's not a misprint, H3PO2, we reduce off the diazonium, and we just have our benzene ring. This is useful if you have put a nitrogen on of some sort to do some other chemistry, and then you want to get rid of it. Take the diazonium, dump in hypophosphorus acid, boom, it's gone. If we take copper 1 chloride in the presence of dilute acid, we can lose this and stick a chlorine on. And by gosh, we can do the same thing with copper 1 bromide. Iodine is so reactive towards diazonium that you don't even need the copper. This group, this and one more we'll see on the next slide, collectively are called the Sandmeyer reaction. Sandmeyer reaction takes diazonium, typically a copper salt, and does a simple substitution. Iodine, like I say, is so reactive you don't even need the copper. Sandmeyer, this is the name to remember. Again, this shows up on multiple choice tests. The other Sandmeyer that we didn't talk about on that slide, copper cyanide, and with KCN. Again, cyanide is going to displace this, and we wind up with a benzonitrile. Now this is real useful, isn't it? Because we know lots of things we can do with nitriles now. So change our nitrogen into a nitrile. If you simply dump this stuff or leave it in acidic water for long enough, what happens is that water will actually attack this carbon and you make phenol. Now, if you took phenol itself and reacted it with the diazonium, this is where we get a coupling reaction. Instead of attacking the carbon here, we're going to attack the nitrogen. Our nucleophile is going to be the benzene ring, believe it or not, and we're going to attack the terminal nitrogen of the diazonium salt. We'll talk about this in detail. This is a coupling reaction again. We've made our bond from the para position here to the terminal end of our azide. The compound we saw earlier, methyl yellow, mellow yellow, that's this reaction. Again, a simple diazonium coupling. All right, let's just take a second and think about how this happens. We know that phenols are very, very, very reactive in electrophilic aromatic substitution, aren't they? Just like amines, aniline itself, very, very, very reactive for the same reason. That is, these electrons can be moved in. We put our electron density on the ring. Do it again. And bottom line, we have really enhanced electron density, ortho, and para to the oxygen. Aniline the same way. Electron density, ortho, and para to the nitrogen. In our coupling reaction, what we're going to use is this source of electrons as our nucleophile. The reaction looks like this. Here's our electron density, attacks the nitrogen, picks up a hydrogen. We get this. Now, because we've used these electrons to make this bond, we have positive charge. We have to get rid of this to get our aromaticity back, and we have coupling. Coupling reactions work really well. You almost always get the para isomer. And again, this is the source for the aniline dyestuff industry. Any questions? All right. Let's pretend that instead of a second-hour exam and a final, I just gave you this problem. If you want an A in organic chemistry, quickly write a synthesis, starting with aniline and making 4-bromo aniline. Okay, you're all up to the challenge, aren't you? Well, okay, we all remember from electrophilic aromatic substitution. All you have to do is take bromine and ferric bromide, right? Do a simple Friedel-Crafts style bromination. However, remember on the previous slide we talked about phenol and the electron density ortho and para. Well, aniline is even more reactive this way. And you don't just make this. In fact, the only product you isolate, where you don't even need the iron, only product you isolate is the tribromo. And you just blew your A in organic chemistry. All right, so how do we fix this? How do we get our A back? We need to introduce a bromine down here. We need something that's not as activating as this, right? But something we can make easily. What if we took this and simply reacted it with an acid chloride? We would make what's lovingly called acetamide. Now the amide is still activating, isn't it? Because we can take these electrons on the nitrogen, move them down, but it's nowhere near as activating as the simple amine or phenol. So now if we took acetamide, we could do our bromination. Our first step here is simply going to put one bromine and only one on the ring in the 4 position. How do we get rid of it now? Because we need aniline. Well, it's an amide, isn't it? If we take an amide and dump it in either acid or base, we hydrolyze off this part, and we're left with the free amine.
Give us a recipe, thank you.
Any questions? It's so reactive that, boom, you get the tribromide. In fact, this is a qualitative test for phenols and aniline. You dump in bromine, a little bit of base, it'll decolorize it just like it was an alkene. Bromine will just add spontaneously. If you only want one bromine, make the amide, do the bromination, and then hydrolyze it back off. And you see how simple it would have been to get an A? Yeah.
So would you be able to turn into diazonium salt first? Would you be able to do that if you had like the NH2 on the ring and then you added the H2SO4?
Sure.
Could you turn into diazonium salt
Absolutely.
and then eventually turn into that?
Well, eventually you could.
I'm saying a
You
couple.
you can't do substitution of the diazonium salt though. Because the diazonium salt, remember, is cationic. It's even more electron withdrawing than a nitro.
You said it would switch it out, wouldn't it?
Yeah.
Like if you
And
add
it would
things to
push it meta, not orthopara. But nice try. All right, that ends chapter 24. Now, Wednesday, we are going to make turkey instead.